regression. Again, you can see this set of slides on Schoology in the tutorial folder. So regression is what we're talking about, a direct causal effect where one continuous variable, let's say height, has an effect on another continuous variable, say weight. So if you shrink someone, they weigh less. If you stretch them up, they weigh more. We're thinking like Ant-Man here, not like a rack or like Gumby or something. So our null hypothesis is that there's no relationship between the two variables, that if you change height, weight doesn't change. If you change how long you study, you don't change what your grade is. That's the null hypothesis. The research hypothesis is that for every increment that you change your independent variable, the dependent variable changes by a predictable amount. And so let's pause for a second and talk about the difference between an independent variable and a dependent variable. We call an independent variable that because you can set the levels of an independent variable before you even collect any data. You can say, I'm going to look at 5 feet tall people, 6 feet tall people, and 7 feet tall people, and you don't even have to measure that. So it's independent of any kind of noise in the system. The dependent variable, you have to measure. So you don't know what those people are going to weigh until you go and find a whole bunch of people that are exactly 5 feet tall, a bunch of people are exactly 6 feet tall, and a bunch of people are exactly 7 feet tall. So that depends on your measurement. And if there is a real regression, then as you change 1 foot at a time, you'll change weight by some relatively constant amount. So regression and correlation are cousins. They both deal with two continuous variables. Regression talks with a causal relationship. Correlation talks about association. Regression is units, so we would say you go up by so many pounds for every foot that your height increases. Correlation is unitless. You just say there's a correlation between height and weight. So since it's got units, it goes from negative infinity to infinity. Correlation is bounded between 1 and negative 1. So regression measures slope. It lets you make direct predictions about the dependent variable based on changes in the independent variable. Correlation measures the strength of association. So it says, well, we think that the dependent variable will change when we change the independent variable by a certain amount, but we don't know the exact number. So cars and noise. If we were doing a regression analysis, we would acquire specific numbers of cars. We would bring them to the traffic light. We would measure the noise that they make. There's significant regression then would be evidence that more cars cause more noise. We controlled the number of cars. In a correlation, you go out at some times, you go to the traffic light and you count the cars and you measure the noise. So you didn't control anything other than you were being there paying attention. And so you couldn't say for sure that the cars caused the noise. You could just say there's an association between cars and noise. So because you didn't control anything, you can't infer any causal relationships. So in a regression, you have two continuous variables, and you have two descriptive statistics. You have the intercept and the slope, because we're basically modeling a line, which I'll show a picture of in a second. And so the expected value of the intercept is the expected value of the dependent variable when the independent variable is 0. So what would someone weigh if they were 0 feet tall? Or how much noise would there be if there were 0 cars? And so what we're expecting to see is a normal distribution around the best fit line. So as you go up, there's a normally distributed amount of noise around where the line thinks the best guess is going to be. So our research hypothesis is that the slope is different from 0. So it's usually a two-tailed hypothesis. It's almost always a two-tailed hypothesis. And the slope is equal to 0 is our null hypothesis. Just like in correlation, the degrees of freedom for our test are the sample size -2, because we have to estimate a mean for each of the two variables. And the test statistic is a t-statistic. It's the regression slope that we found divided by the standard error. And you're either going to use SPSS or the spreadsheet I make for you to calculate your test statistic You're not going to actually have to compute that yourself, so don't worry about it. You can see what the computation is if you want to explore the formulas. So evaluating regression, you look at the p-value, as always. The p-value is the probability of observing our slope if the true slope, the true relationship between the two variables, is actually 0. So we reject the null hypothesis with a significant result, and that suggests that changing the independent variable by 1 unit changes the dependent variable by this slope coefficient b. So that's actually b1. Let's change that. There we go, b1. Good times. Non-significant result means that we reject the research hypothesis and that we don't think there will be any effect on the dependent variable when the independent variable changes. So here's a little toy example I made with some toy car data. So you can see as the number of cars increases, the sound increases by about 3 decibels per car. So the slope of this line is about 3. The intercept is going to go back down to probably around 0. And you can see that there's a little variation around the predictions at each point. And so when we would report that, is you say a sentence like, the number of independent variable caused a significant increase, in this case, in the description of the dependent variable. And then you write the literal word slope plus standard error, an equal sign. And then you write your slope, and you write your standard error, and you write the units. And there's a comma, and you say t degrees of freedom equals your t statistic, p equals, and your p-value. So that's how you report a regression.